Okay guys, today what we're going to do is we're going to take the concepts of tension and apparent weight and we're going to kind of push them to a higher level. We're going to be moving into two things here, equilibrium today, and then we'll be doing some non-equilibrium stuff here in a bit. Okay? Now equilibrium, guys, is a super easy concept. We talked about it when you were freshmen, and the definition is right up here. The sum of the forces on the object is zero. Which another way to say that is the net force on the object is zero. And then because of Newton's second law, we all know that F equals ma. And if you do not have a force, or your force is equal to zero, what's going to be your acceleration? Zero. So we can also say that the object is not accelerating. Okay? And when it's not accelerating, I want you to make sure you understand both these situations. It can be stationary. It can just be sitting there doing what it's doing. That thing is not accelerating. Now, if I move it at a constant velocity, then it is not accelerating as well. And so an object can be in equilibrium if it's moving. Okay? It just has to be moving at a constant velocity. Remember we dropped the coffee filter and the coffee filter hit terminal velocity and then it was just going at a constant velocity? Okay? The sum of the forces on that object at that point we would know would be zero. Weight pulling down, counteracted by air resistance pushing up, and so that object was in equilibrium. Okay? This object right there, that pen, is in equilibrium. You're in equilibrium right now because weight's pushing you down and your desk is pushing you up, equal and opposite. Okay? Make sense? Now, equilibrium, I think, is a pretty easy concept. We can use it to solve some pretty complex problems. Like in this case, we've worked on this yesterday in the when we were talking about apparent weight and tension. What is the tension in the string? In this case, we got a 100-kilogram block hanging off a cable. We know that the weight of that, okay, is going to be 100 times 9.8, or mg. That's what's pulling down, and the tension is pulling up. If this thing is not accelerating, we can sum the forces on it and set them equal to zero. So the sum of the forces is zero. We know the force going down is 100 times negative 9.8, which gives us negative 980, plus t going up, and then we can use that to solve for t, so t turns out to be 980 newtons, which that is really straightforward and easy. We've done that enough that that should be kind of really second nature. Okay? Now, when we move from here, which is a simple problem, to over here, this gets a little tougher, but the concepts are the same. We just got to use our vector trig stuff. Before we go there, though, I probably should have done an example 3, but we can kind of just throw it in right now. What would happen if I add another cable right there? Well, we had T, right? Let's call that T1. Now we're going to add another cable, which should give us, that one's going to have tension in it as well, right? Okay. What happens to the tension when we just double the cables? If they're both pulling straight up. Will they get cut in half? Okay. Does that make sense to everybody? And so what we'd have is something like this. Instead of, we'd have 0 equals 100 times negative 9.8 plus T1 plus T2. And guys, this is a concept I want you to make sure you get. If we have two strings, then they're going to separate the tension equally if they're both pulling up at the same angle. Okay? Does that make sense? Now I will throw this at you. If we have a sine like this and we hang it like that and we hang it like that, and both these angles right here are 45. If those angles are the same, then guess what we can say about the tension in the string? So tension 1, they would be equal to each other. Okay. Which would mean the strings would have to be the same length if that sine's gonna hang at the same angle, right? Okay. Does that kind of make sense? Now let's get to an example where the strings aren't the same length and therefore the strings are going to hang, they're going to have different angles. And let's look at this one. And this one's pretty important, guys. This one's one that kids struggle with, but it's not really that hard. So let's go ahead and look at this. We have a 200 kilogram sign hanging off of 2 cables. And let's call this cable 1. Let's call this cable 2. Are those cables going to pull in this direction, up that way? Okay. And so what I've done is I've taken this and I've redrawn it as a free body diagram. Okay, so if you guys can follow this, here's my sign as a dot. That's what we do with free body diagrams. Here's the weight, and I think you guys would all agree that the weight is equal to 200 times 9.8, which is 1960. Pretty easy, straightforward stuff. Okay, this is T1, this is T2. Guys, if that's 45, can I say that that's 45 due to alternate interior angles? Okay, so I'm going to put 45 there. Same thing here. If that's 35, is this 35? Okay. Now, I think you guys, this is a simple trick. You guys would agree that this component right here is going to be opposite. So we'd go sine 45 times T2 would give me that component, which is really, could we say T2 in the y direction? Okay. And then this component here is going to be T2 in the x direction. And then we could do the same thing here. This is going to be T1 x, and then I'm running out of space. T2x is going to be equal to that. Oh, you know what? I'm sorry, I put x there. This should be, let me do this again, T1y. Let's try that. Okay? Now, really, really simple, guys. When you're in equilibrium, you're going to always sum the forces and set them equal to what? 0. So if you look, I've summed the forces in the x and set it equal to 0, and I've summed the forces in the y and set them equal to 0. Okay? Once you've drawn a free body diagram and you have all your forces cataloged, then this problem becomes a pretty easy problem, except for the fact you got to do a lot of calculator work. Okay? Now, guys, I think you guys would agree with me. In the x direction, that's all we have is this component and that component. And if those are the only 2 components in the x direction, we know they basically have to be equal to each other because they're pointing in the opposite direction. But another way to write that is this. Sum of the forces in the x is 0. So 0 equals cosine 45 T2, and that's in the positive direction, minus, or plus, a negative if you will, cosine 35 T1. That is the equation that would come from sum of the forces and set them equal to 0. Everybody see that? Now, we're going to come back to this piece in a second. Let's sum the forces in the y. They are equal to 0. So we say 0 equals, we have sine 35 T1, that's going up right there. We have sine 45 T2, that's going up in the positive direction right there. So we're going to add that plus that, and then we're going to subtract, or plus a negative, subtract 1960, and that should give us something that equals 0. Everybody cool? Does that make sense? Okay. This is rudimentary statics, which means it's not accelerating. So if we look here, guys, what we have, I'm going to do this in blue. At this point, we have that equation, and we have this equation. Right there. Which means we have 2 equations and 2 unknowns. Okay. Now, one of the reasons you took, what, Algebra 2? Is to figure out how to solve systems of equations. When you have 2 equations, 2 unknowns, one of the ways you can solve those is substitution, right? And so you'll notice what I did here is I solved for T1. I took this over on the other side, made it a positive, and then I divided by cosine 35, which got T1 all by itself. Does that kind of make sense? So if I know that T1 equals that. What can I do when I come down into this equation? Can I substitute it? Okay. So what I did is T1, instead of putting T1, I put in sine 45 T2 cosine 35, which you can see right there. When I do that, it gives us how many variables in that equation? One variable, and then we solve. Okay. Now what I did is I did all the math for you, and we come up with T2 equals 1630.306 newtons. Okay. That's our tension in string 2. And then I'm going to use that, bring it up here, and substitute it back into this equation for T2. And when I substitute it in for T2, we come up with a tension 1 of 1407.31 newtons. Okay. So we know what the tension in this string is going to be, okay, which is 1630. And we know what the tension in that string is going to be, which is 1407. Okay? Now, a good way to check this is, guys, if I took, since T1 is this, if I take that times the sine of 35, and I take this value times the sine of 45, and I add those two things together, I better get what? I better get 1960, because that sine is not accelerating. It is sitting there, so it has to be in equilibrium. Okay? And I always like, for me, I always like having a check at the end, and so that's how I would check this problem to make sure I have not made any silly math errors. Okay? So to review, equilibrium problems, whenever it says it's not accelerating, or it's sitting still, or it is moving at a constant velocity, that means it's in equilibrium. And when it's in equilibrium, you can apply the problem-solving strategy where you sum all the forces and set them equal to 0. If they're acting in one direction, that's just real easy. Sum them, set them equal to 0. If you have weird angles, that's where we kind of get into the vector nature of this. You're going to have to sum the x's and set them equal to 0, sum the y forces and set them equal to 0. And guys, a lot of times in these problems, you're going to end up with 2 equations and 2 unknowns, which is, I mean, that's pretty simple math. You guys should be able to rock that. Okay? All right, that's equilibrium.